This is the video lecture for the Rockets lesson plan. It was created and narrated by Sean Krupa and uses original material from Andrew Long. This video and accompanying lesson plan are part of Ohio University's Boat of Knowledge in the Science Classroom project, funded by the National Science Foundation. What is a rocket? As you're watching this video, think of your definition for what a rocket is, and we'll come back to this at the end. Before we go any further, let's review some history of rockets. As far back as 400 BC in ancient Greece, records exist of steam being used to propel objects. And when gunpowder was invented between the 1st and century AD in China, this advanced rocket technology even further. In fact, it was 1200 AD, also in China, that gunpowder filled tubes attached to bamboo rods resembled the first rockets. Rocket technology advanced between the 15th and 19th century in Europe. This included the invention of the first multi-stage rocket, as well as Newton working out his laws of motion, which led to experimentation, and finally the use of rockets in military engagements. Modern rockets first started showing up around the beginning of the 20th century. It was Konstantin Tsiolkovsky that first suggested that rockets might someday be used for space travel. Robert Goddard experimented with solid and liquid rocket fuel and would go on to be known as the father of modern rocketry. And finally, Germany's Wernher von Braun invented his V-2 rocket, which was miles ahead, technically, of any other rocket at its time. It had liquid fuel and was gyroscope directed. It could level an entire city block. After World War II, von Braun would go on to work for the United States government and NASA. After World War II, rocket and missile technology grew exponentially. Most of this, unfortunately, was due to the Cold War between the United States and Russia, the invention of intercontinental ballistic missiles to carry nuclear payloads, and the space race drove rocket technology and development. Now let's talk about the physics of rockets. Rockets are a good subject because they include many areas of physics. Before we go any further, you'll need these equations when working through the example problems. Pause this video to write down the equations. You can resume when you're ready to continue. Let's start with potential and kinetic energy. Rocket operation can be thought of as energy transformation. Is the energy in the rocket fuel potential or kinetic energy? If you said potential energy, you're correct. The energy stored in the fuel is a form of potential energy, and this gets transformed into the motion of the rocket and the height of the rocket. Is the motion of the rocket potential or kinetic energy? And is the height of the rocket potential or kinetic energy? If you answered that the motion of the rocket is kinetic energy and the height of the rocket is potential energy, you're correct. As we see, no energy is created or removed from the system. It's merely transformed. Let's do an example problem. How much fuel must a 500 kilogram rocket carry to reach a top speed of 12.4 kilometers per second and an altitude of 1,600 kilometers? Typical rocket fuel has an energy density of 1 times 10 to the 7 joules per kilogram. And for the purpose of this example, ignore the weight of the fuel. Take a few minutes to work on this problem, and when you're ready to see the solution, resume the video. The answer is 4,600 kilograms of fuel. Step 1 begins by figuring out how much energy we need. Remember, we said that the potential energy in the fuel had to be enough to supply the kinetic and potential energy of the rocket. Therefore, we need to figure out the kinetic energy of the rocket at its final speed, plus the potential energy of the rocket at its final height. Using our equations for kinetic and potential energy, and using the values given in the problem, we figure out that we need 4.6 times 10 to the 10 joules of energy. In step 2, we answer how much fuel is needed. We just calculated how much energy is needed, and in the problem we were given the energy density, which is the amount of energy per mass of fuel. If we take the energy we just calculated and divide it by the energy density, we get an answer of 4,600 kilograms of fuel. Now let's talk about momentum. Can we explain rocket flight another way? Let's talk about momentum conservation. Momentum, we know, is symbolized by the letter P and is equal to the mass of an object times its velocity. Remember, velocity is a vector. Therefore, momentum is also a vector. That means that the direction matters. Conservation of momentum says that the total momentum of a system must be conserved. This lets us write that P initial must be equal to P final. And writing that out in its components, we have the initial mass times the initial velocity must be equal to the final mass times the final velocity. Let's do an interactive example. Here we see a water rocket. Water rockets work by pressurizing water and then releasing it. What is the total mass of this rocket? If you answered that it's the mass of the shell plus the mass of the water, you're correct. What is the total momentum of the system? It's 0. It's just sitting there. Therefore, V is 0 for the shell and the water. And when you work out the equation, which is very simple, we get 0 plus 0. After launch, however, the water starts to exit the backside of the rocket. What is the total momentum of this system? It's still 0. It must always be 0 since momentum is conserved. But what has changed? The velocity of the shell is no longer equal to the velocity of the water, which is no longer 0. The rocket and the shell are moving one direction, while the water's mass is moving another direction. Therefore, we can rewrite our momentum conservation as being equal to the mass of the shell times the velocity of the shell must be equal to the mass of the water times the velocity of the water. Since the water's velocity is in the opposite direction, it has a negative sign, and we can put it on the other side of the equation. This is also another way of describing Newton's third law. Now let's do another example. A rocket shell is made from an empty 2-liter bottle and weighs 15 grams while holding 275 grams of water. After launch, the speed of the shell was measured to be 16 meters per second just after it runs out of water. What is the speed of water exiting the rocket? Pause this video now to work through this example problem. When you're ready to see the solution, resume the video. The answer is 0.87 meters per second. Step 1 is to answer what is the momentum of the empty shell. Remember, we said momentum was mass times velocity. Working this out, we get 0.24 kilograms times meters per second. In step 2, we answer what is the speed of the exiting water. Remember our momentum conservation relation. This allowed us to write the equation mass of the shell times velocity of the shell is equal to mass of the water times velocity of the water. Rearranging and solving for the velocity of the water, we get our answer of 0.87 meters per second. Now let's talk about drag and aerodynamics. Let's look at some factors that affect aerodynamics. We'll focus mainly on the shape and size and velocity of an object. And on the right in the slide, we see the drag equation. It looks complicated, but it's not really. Drag is equal to some coefficient times the density of air or liquid times the velocity of the rocket squared divided by 2 times the reference area. The coefficient CD is complex and depends on a lot of factors related to the object. Therefore, it's usually just measured experimentally. There are a few things we need to take into consideration. One is that we see that the drag force is dependent upon the area. Therefore, it makes sense that a rocket's slender shape is useful because it minimizes the area. Second of all, the drag is proportional to the velocity squared. This means that if you double your velocity, your drag force increases by 4 and not 2. Finally, as rho goes to 0, drag goes to 0. This is why there's no drag in outer space. Let's do another example. An engineering student has to choose whether to build their water rocket out of a 2-liter bottle or a 16-ounce bottle. The 2-liter bottle has a radius of 5 centimeters and can be pressurized to reach a speed of 14 meters per second. The 16-ounce bottle has a radius of 3.5 centimeters and can reach a speed of 18 meters per second. Which bottle will make a rocket with a smaller drag force, and how much smaller will it be? For this problem, let 1/2 times the coefficient times rho be equal to 1. Take some time to work through this example problem. You can pause the video and resume it when you're ready to continue and see the solution. The solution is that the 16-ounce bottle will have a smaller drag force, and it will be 19% smaller. Step 1, we have to calculate what is the drag force of the 2-liter bottle. Using our equation for drag and working out the surface area of a circle with radius of 5 centimeters, we get a drag force of 1.54 newtons. Similarly, we calculate the drag force for the 16-ounce bottle. It has a different radius and a different velocity. This works out to a drag force of 1.25 newtons. How much smaller is the 16-ounce bottle's drag force? If we take 1 minus the 16-ounce bottle's drag force divided by the 2-liter bottle's drag force, we get 0.1883, which is about 19%. The last topic we're going to cover is gravity and escape velocity. If you wish to launch an object from the surface of a planet, you have to make it accelerate to some minimum velocity, or else it'll just fall back to Earth. This velocity is known as the escape velocity, and we can derive it easily. We'll set the kinetic energy of an object equal to a planet's gravity. We notice that the small mass, or the mass of the object, cancels on both sides. This means that an escape velocity is not a function of the object you wish to launch. An escape velocity is a property belonging to the planet itself. Solving for velocity, we get an expression that velocity equals the square root of 2 times the gravitational constant times the mass of the planet divided by the radius of the planet. This gives us our escape velocity, or the minimum velocity required to leave a planet's gravity, as we previously mentioned. Let's do another example. We're going to calculate the escape velocity for the Earth. You'll need the following information about the Earth: its mass, its average radius, and the gravitational constant. Take a few moments to work on this. You can pause this video and resume when you're ready to see the solution. The answer is 11.2 kilometers per second, or 1.12 times 10 to the 4th meters per second. The picture below shows what happens when you launch with different velocities. If you launch with a velocity less than the escape velocity, you plunge back to Earth. If you launch with a velocity greater than that of the escape velocity, you can get an elliptical orbit or break orbit from the Earth entirely. And finally, if you launch with exactly the escape velocity, you get a perfectly circular orbit. In conclusion, we see that rocket technology has evolved from 400 BC to present time, and continue to evolve today. Also, we looked at rockets as they pertain to many areas of physics, including energy, momentum, Newton's laws of motion, and gravity. So, back to our original question: what is a rocket? Hopefully you thought of your answer. The dictionary tells us that a rocket is any object which uses a controlled release of stored energy as a means of propulsion. This concludes the video lecture for the rockets lesson plan. Thanks for your attention.